let's review. Oh, I do want to say one thing. I am going to have to end class a little bit early on Thursday, probably around 4:30. I'm really sorry about that. But we need to start working on this satellite project down in San Francisco that I told you guys about. So what's the best way to answer the question at the center of really any scientific debate? But what's the best way to answer the question about the sun that we're talking about? It's obviously to go to the sun. And so we've got a pretty enthusiastic and sophisticated community that's really interested in that topic too. We're also just interested in how to build satellites that can cruise around the solar system and accomplish all sorts of cool stuff. And right now, the only people that do that are these big state institutions like NASA and stuff, and they're very slow and expensive. And we're going to see if we can build a better platform so we can have some sort of maybe more open-ended platform for people to go explore the solar system. Last semester, we talked a lot about space mining, which is probably going to be a pretty big deal soon. There's a ton of really, really otherwise rare and expensive metals drifting around in the solar system, and I think we're going to see a lot of industry related to that. But they don't have a very good platform for how to actually go and explore. Of course, like I said, they're depending on these really bulky, slow, creaky state institutions to build spacecraft. They spend way too much money. It takes way too much time. So the satellite project is in some sense oriented towards even bigger questions than the science that we're talking about in this course. So anyways, Dr. Benenberry and I got to go down to San Francisco on Thursday, and it might happen a couple other times this semester, but I'm going to try really hard to be here for class, even if I got to bounce a little early. Yeah.
As you guys kind of plan it out, could you keep us updated?
Heck yeah.
Just minor things. I'd be curious on seeing your progress as it goes.
Absolutely. Yeah. And it's really fun too, because this is something that you guys get a cool front row seat for. We're not even really talking too much about this on our podcast. It's very, of course, everybody wants it to work out before there's a lot of publicity about it. And we're still in the early stages and getting the team assembled. And, there's a chance of embarrassment if things fail. So you guys are definitely right here in the front rows. And yeah, I mean, I upload these videos to a YouTube channel, but nobody knows about it, basically. And so we don't really, it's a very quiet corner of the internet where these videos of these lectures are hosted. So yeah, it's happening.
Drag it up and use it against you at some point in time.
Yeah, well, we'll worry about that then. That's much later. I'm sure we'll start publicizing this. So one of the other cool things is I've got a buddy who's actually a professional documentarian, filmmaker, all that stuff. He's going to start working on a documentary about the whole project that'll unfold over the next few years. So hopefully you can show all your friends about it on Netflix 5 years from now or something like that. Should be pretty cool. What else? Okay, so that's happening. Again, somebody remind us about the core crisis that we're talking about in this class, at the core of the stars, which from downstream flows, starts at our sun, but of course reflects the stars in general. What is the central crisis we've been discussing? Can somebody just remind the class? I'm looking to these people in the back. I really want to make sure everybody in this course walks away understanding this one crucial issue. Yeah.
Would be whether it's a fluid or a gas. That's the stuff.
Fluids, the word fluid is not quite right. Liquid, let's say liquid. Because liquid is, yeah, gases can be treated as fluids. Fluid is really just something that flows. It's different than a phase state of matter. So it's different than the actual arrangement of the atoms with respect to each other. So yeah, the central crisis is really the state of the stars. Let's try to go one step deeper than that, though. Who cares? Why does it matter? Yeah, Owen. That's a really good reason, yeah. Can you elaborate on it at all?
You want to find out how the sun does what it does.
That's right, yeah. That's a huge piece of this puzzle, right? So, of course, how do we power our civilization here on Earth?
Stuff.
By burning stuff, which is kind of gross. The sun generates incredible amounts of power, and it's so powerful you can't even look at it. And we don't really seem to know how to make that happen here on Earth. But if we did, it would be a complete revolution. I mean, the limiting cost in literally everything from building this building to running this building to running this school to literally everything comes down to a bottleneck of energy. Energy is the most expensive thing on the planet, really. Just powering all these processes is really, really expensive. The fuel for fusion is hydrogen, which means you can get it out of water, right? It's one of the most abundant elements on the planet. It's certainly the most abundant element in the universe. And so this is gonna happen, I believe. I don't know when or how, but I do know that as long as we understand fusion to be a process that happens in gaseous balls, we're probably not going to achieve anything useful about it here on Earth. So that's a really good point. And I think that that's a good one to lead with in terms of why this discussion really matters. Now, why it matters in terms of the science hasn't become totally clear in this course yet, because we're going to see, and maybe you guys have, the textbook has kind of gotten out in front of us at this point, if you're following along with the quizzes and everything, you're going to start to see that the stories about the lives and deaths of stars is radically different with liquid stars versus gaseous stars. And so that's going to become apparent maybe in another week or two when we move beyond the sun itself and start talking about stars as a whole class of entities. Yeah, Dante.
Quick question. I don't know if it's a quick question.
It's all good.
Um, is one of the things that just wouldn't exist with like, or would black holes be a thing without the like infinitely compressible stars?
So I want to spend a whole class doing black holes at some point. So you're right, though. Black holes are a downstream consequence of the collapse of large stars. Now, the really, really crazy thing about liquid stars is that unlike gases, liquids are essentially incompressible. So the story that we end up telling about what happens to stars as they age and cool off is very, very, very different with a gaseous model versus a liquid model. So we're going to find out, and we're going to go into all the nitty-gritty details of this, but we're going to find out that the standard story of what happens to a star is when it kind of gets old, since the fusion in the standard gaseous model is only happening at this really hot point at the center of the star, eventually, and it's also supplying the pressure that keeps the star, supported, let's say, that when that burns out in the standard model, the star starts to fall into itself. And this process continues, ad infinitum, because gases, ideal gases upon which the equations of state for the stars are modeled, they're indefinitely compressible. And so you get to these kind of physical, you really get to points in the compression of these enormous, massive objects where you kind of exceed the physical limits of modeling. And the black hole that you've heard about in all the movies and everything is one such example. There's many of these such examples. Neutron stars, white dwarfs, they all require a completely different story when it comes to the liquid model. But we have answers for those things too. So at the end of the day, you can compare and contrast these two stories, but they are radically different. And even the entire meta story of the universe, the cosmology, changes radically based on this material reconception of light. Really, that particular light that I showed you on the first class, that particular rainbow of light that we see from stars, But that's kind of come down at the end of the course when we start talking about cosmology a bit more. Questions about this paradigm shift that is perhaps under our feet. So it's quite exciting. If this, depending on how all of this proves out, it could be perhaps the most exciting thing in this wing of science since Copernicus and Galileo and all of these things, when we had to reimagine the solar system radically with the Earth not at the center of things, which I think was quite traumatic for the astronomers at the time. But it did happen, and we're okay, and everybody moved on, and it wasn't an apocalypse. It was just a scientific revolution. Okay. So anyways, to wrap that conversation, so it's actually quite easy to test in some sense if you can get a space probe to the sun, because the sun isn't supposed to have a surface, right? So that thing that we keep referring to as the surface, and even your textbook keeps calling it a surface, the fine points is that you'll find it's an optical illusion where the gas becomes not thick enough that it can let some of the light out. And we see this thing that we're told is an optical illusion at the surface. Now, just to impress upon you how obvious it should be whether there's a surface when we get there or not. That photosphere, the photosphere is the light emitting not surface of the sun, let's say. It's supposed to be 10,000 times less dense than our atmosphere at sea level. Now, if it's a liquid, it's probably about as dense as water. And the whole sun is probably more or less on that same order of density. There may be some crystal rearrangement in the core, and we'll talk about that today. But in other words, when you splash a probe into the surface of the ocean, there's going to be a crazy deceleration, right? But if you just fly a probe into a region that's 10,000 times, that's literally more of a vacuum than we can produce in laboratories on Earth, 10,000 times less than our own atmosphere, you wouldn't feel anything. It's not even going to decelerate. Nothing should happen, right? So it's a pretty easy question to answer if you can get your probe all the way out there and crash it into the sun. You should be able to see the thing through your instrumentation if it's, even halfway sophisticated. It's not an easy task. Obviously, it's very hot and it's very bright, and getting communications established and all of that is a bit of a nightmare. But engineering geniuses love nightmare problems to solve. Yeah.
Is that kind of the idea of how your group is going to try and prove or disprove the liquid theory?
That's it. That should be all it takes, yeah. It sounds simple. Technically, I think it's quite challenging, but we're really encouraged by the talent that we have already interested in the project. So could be pretty cool. And like I said, it might extend even to a bigger project, which is really just how to create cheap, for lack of a better word, space drones that can explore the solar system far more effectively and efficiently than the state bureaucracies have been able to mount so far. You've probably noticed that SpaceX has basically taken over the launch industry in this country. And that's because, these kind of maverick entrepreneurs have the ability to move really fast. They can destroy things, they can make decisions really quickly, they can crash a bunch of rockets. You don't have to go through all these very slow, laborious institutional bureaucracies to get things done. So it's pretty cool. It's really, really freaking exciting, honestly. But it's just the early phases, so we'll keep in touch about that. But yeah, we'll have to duck out a little bit early on Thursday to catch this plane at 6 or whatever it is, 6:30, something like that. Okay, let's continue with our examination. So today, let's try to finish up the basics of the solar structure. We'll be re-examining all these little pieces in sort of their fine details as they crop up in our story. But I want to sort of build out a picture of the layered structure of the sun today. This is actually a picture from your textbook. So we're going to be talking about this model in contrast to the liquid model, of course, which is a little bit different. It's actually not horrendously different. The only we'll see some differences crop up. We will need to talk about magnets a little bit in order to make sense of some things about the sun, and hopefully we'll get to that today. That will require us to go back and think a little bit more about atoms, which I know will probably terrify some people, but I did go through all of that effort, wasting an entire class or two to talk about atoms, because it turns out that you can't understand a magnet without understanding atoms. Unfortunately, just like our mathematical atom, our concept of magnetism in modern physics is deeply mathematical. So I'm going to try to sort of surpass that, or at least complement it with some material picture of what atoms might be doing to each other to do that magic that we feel when we put two magnets together. How the heck does that happen? Turns out that there's actually a pretty easy way to think about it, and it could be so. At least it's going to help us get a picture of how it could be materially happening other than magic. So we got to talk about that, because we got to talk about how these sunspots work today. We got to talk about how the solar cycles work. I don't know if you guys realize we're at the peak of a solar cycle right now. That means the sun is super awake and super active and has all sorts of flares. And I think we just got smashed with a solar flare either today or yesterday, really recently. It's been kicking off a lot of flares if you're paying attention to the science news or anything like that. So we're going to talk about how all that happens. Yeah.
I've not heard anything about a solar flare. Did it affect much when it hit us?
We're able
Yeah.
to see the northern
The
lights
internet-
there yesterday. and today.
Wait, you can see the northern lights.
Yes.
Oh.
That's awesome.
But I also had like a lot of Wi-Fi and connection issues.
Interesting.
And I do remember from my high school astronomy class, we talked a little bit about CMEs and all that and how it affects the internet.
Yeah. So
I just
we'll get to that. There was the last time. So the nice thing is that the Earth is a little tiny target, right? And the sun is spraying all of this matter, most of it hydrogen, honestly, which is somehow flying off the surface. Of course, you have two very different stories of why that's happening with a liquid versus a gaseous star. We'll talk about that. But anyways, it's spraying all this stuff. Sometimes huge chunks of this stuff fly off, right? Most of the time, it misses the Earth. It's kind of happens all the time, mostly at these solar maximums. We're going to talk about what a solar maximum is, but the last time we got completely head-on smashed by one of these things was in the 1800s. It was a really crazy period because it was right at the birth of telecommunications. Before really radio communication was a big deal, they were doing this thing called telegraphs. It's funny, I've probably used that word 3 times in my life. Telegraphs, which were these wired connections where you would kind of talk in chirps, little Morse code signals to each other. And the event was so electromagnetically disturbing to the planet that it actually cooked a lot of those telegraph lines and caused all sorts of chaos. So you can only imagine what would happen if that hit our current electromagnetically powerful civilization that we have today, where basically everything depends on electromagnetic communication, everything from our power grid to our internet. It could be a real problem. And so not to freak you guys out or anything, but it is something that I know from people I know at NASA and stuff that they're working on it and they're trying to find a way around that. But it is a serious issue, and understanding the solar cycles and understanding the sun is really, really important to being able to predict that space weather and, in some sense, safety ourselves against it. Yeah, both of you guys, one at a time though.
You can go for it.
telegraphs are telegrams, right? Or
Telegram, I think the gram is what is sent. The graph is the machine or the technology itself. Yeah.
okay. Oh,
Yeah.
I guess a bit more of a question about coronal mass ejection themselves, but like in that case of where it just fried those telegraph like wires and stuff, there must have been like a lot of energy with that, right? Or
Yeah, an incredible amount of energy. Let's circle back on this because I want you guys to understand how this happens and why there's so much energy tied up in these. And to understand that, we have to understand the magnetic structure of the sun, because the reality is that these solar cycle, when we say solar cycle, what we mean is that the polarity of the sun's magnetism inverts every 11 years, which is really, really fast. Now, it happens with our Earth too, but it takes on the order of 1 million years for that to happen on Earth. Really, really slow. But the sun is constantly changing polarity of its magnetism. So we have to understand what magnetism is, what polarity of magnets means in terms of what the atoms are doing, and then maybe we can understand why the sun does it. And it might help us understand what's happening at the surface to generate these flares, to generate these coronal mass ejections. All that kind of flows downstream of understanding how the magnets themselves work inside the sun. Yeah.
Apparently you'll be able to see the northern lights tonight as well.
Oh, cool. Northern Lights, everybody. I've never seen them before. We're literally living under a cloud up in Grants Pass where I live, so I will not be seeing any of that. You guys down here with your pristine weather can enjoy the light show.
Until the clouds roll in.
But that's crazy that it would extend all the way down here. What's that, Kevin?
Until the clouds roll in.
Until the clouds roll in. Yeah, maybe you'll get to see it.
There's
You
a
have a
giant G4, so what they call a coronal mass ejection.
good times. Yeah, hopefully it won't mess with any of the electronics too much. Again, it has to be a real direct hit like the Carrington event for it to be a real nightmare, I think. So that happened, what, 150, almost 200 years ago. So yeah, is it?
What's the chances that like an event like that will happen in our life?
Yeah, I mean, probabilistic determinants are very difficult because they require you to understand uh, the background likelihood. We only have one recorded event of this happening, probably because people prior to the technological age, the electromagnetic age, maybe they experienced some crazy northern lights or something, but it didn't fry their equipment because they didn't have such equipment. Yeah.
Well, technically, one almost as big as the one in the 1850s. What happened in 2012? It just like barely missed Earth.
Exactly. As long as it barely misses us, we're good. We'll just get some increased activity and.
But yeah, if it did hit us, we'd still be recovering to this day. Most of our satellites probably wouldn't be functioning.
Yeah, I mean, it could be really, really bad. I mean, I know there's a lot of really smart people working on what to do. And last time I checked in on the problem, talked to a couple of really high up people at NASA about this, and the project essentially involved ways of disconnecting the grid nodes from one another. So do you guys know about power grids and telecommunication grids? So it's basically, you can think of it as a net that's literally draped across the Earth. So, say for whatever reason, Portland needs a little extra power one day. It's able to draw power from other townships and other power plants outside of Portland, right? And then it can also pump power out to them if they don't want to have to run their power generators and things like that. Basically, the whole world, at least individual countries, are connected on power grids that are, in some sense, decentralized and able to share. The same goes for telecommunications. So if you're able to insulate one from the other, the Earth is turning, right? So it's turning into the sun. You probably noticed every morning. As long as you can keep yourself insulated in that moment when you're actually receiving the flare, you should be able to cause minimal damage to the disk, to the shaded areas of the world, and you should be able to kind of tune where that direct hit smashes into you and really minimize the damage. I mean, I think it will be quite destructive, but I think that it doesn't have to be catastrophic to the civilization. Yeah.
I feel like the best solution, I feel like the easiest solutions are either make a giant mirror that reflects all the sun,
As a big mirror, man.
or just turn the sun off.
Don't do that. We're gonna need that sun. Okay, we're gonna come back to all this, so you can put this on the back burner because we'll be talking about this. But we have to understand how these things happen. I think before we think too much about how to mitigate them. And in all honesty, I haven't really revisited the mitigation in quite a few years, but people are working on it. That's the good news. Let's finish up the solar structure a bit, and then let's see if we can make sense of magnets. And that would be, I think, a heck of an accomplishment for today. What about any questions about what we did last? Let's kind of review, actually. That's probably a good idea. Let's review what we talked about so far with the solar structure, because there's some important pieces I don't want to miss. And plus, I need to still learn a bunch of your names. And so, yeah, guys, tell me anything you remember about the solar structure from last time. Anybody? Don't be shy. I know it's been a long weekend. You guys were thinking about anything else? Yeah. Is it Dylan?
Yeah. Sunspots are cooler in temperature compared to the rest of the photosphere.
That is definitely what your textbook says. I am not totally convinced that is the case, and I will build out an argument for that in just a moment. But yes, they are definitely darker. Sunspots are darker. We didn't quite get to sunspots last time. What did we talk about last time? We talked about faculae. You guys remember? Anybody remember what faculae were? We talked about the metallicity of the surface, the solar limb darkening. Anybody remember anything about that? They're super technical concepts. It's all right. Dante, yeah.
When you look at an image of the surface of the sun without the atmosphere, the edges of it gets darker as you go toward the edge, and it's brighter as you go toward the center. And you see this on Earth when metals are heated up really, really, really hot.
You see it actually with metals and with nonmetals, but yeah, any condensed matter will do the same effect. Yeah.
But you don't see, but with gases, they just glow.
Yep. So that's going to play into understanding the sunspots a little bit too. I really wanted to, the metallicity stuff is perhaps more important for sunspots. So actually, let me just show you this, just remind you of this. So as you can see, this is the angle that you're viewing something from. So if you're looking at it from the side, that's 90 degrees. So actually the emissions of heated liquids and solids on Earth, they actually fall off at 90 degrees. So they actually they have very little emissions out to the side. This is just a principle of thermal emission. But there is a difference when you look at them head on between metals and non-metals. And you guys are familiar with this because the opposite of emissivity is reflectivity, right?
Metals
So-
are very reflective.
Right, metals are really reflective when you look at them head on. That's why the emissivity is so low for metals head on. Now, I'm going to invoke that to consider what we might be looking at when we look at sunspots in alternative to the textbook explanation that they're just cold, which is possible. It is possible they're colder. It doesn't seem to be completely obvious because no one's been able to get the resolution to do an actual broadband analysis of the light coming off of sunspots. They're too small, the telescopes aren't powerful enough. So we only have individual frequencies, right? And so we can't totally make that nice black body curve off of a sunspot, which means we can't get the real temperature of it. So we don't know if it's the temperature or if they're just darker, which is a possibility as well. So, you know, one of the things that's really obvious about, so let's just look at this basic floor plan. Let's just roll with this. So this is from your textbook. I think it's from your textbook anyways. Yeah.
It is.
It is, nice. Well, one of the funny parts about it, of course, is I highlighted it in green there. You know, from the visible surface of the sun's not supposed to have a surface if it's a gas. So that's kind of a funny play on language. But anyways, more importantly, let's look at this general idea. One thing that you'll notice is that right below the surface, there's supposed to be this area of convection. What is convection? Anybody know? You guys have probably seen this before. Anybody like cooking? Like, yeah, so you've probably seen this kind of thing, right? When do you see convection when you're cooking?
In an oven.
Well, convection ovens are a thing, but when can you actually see the effects of convection? Anybody?
When you're boiling water.
Yeah. So when you're boiling water, what happens is you actually have these bubbles roiling up from the surface, right? And then actually, if you look at it carefully, you can look at videos on YouTube where they have dyes and stuff. You actually see these little cells, just like these little circles that they show, right? The stuff boils up, the cold stuff kind of sinks down, and you get these kind of cycles, right?
It's usually the hot is up toward the edge and then it comes back toward the center. It just keeps doing it.
Exactly, yeah. These are actually called Bernard convection cells, but that doesn't really matter. The point is, when we look at the surface of the sun, we see those same sort of little bubbly things that you see when you're cooking something on the stovetop, right? They're called granules. And the same principle applies. So from the picture of that, and of course this is a sunspot on the right, we'll deal with sunspots in a second. From that, astronomers, astrophysicists have inferred that there's a convection zone directly below the photosphere, right? The visible surface. Okay, so below this convection zone, whether it's a gas or a liquid, there's thought to be another mysterious zone, which is called the radiative zone. This is, of course, where in the textbook story, the light bounces around for millions of years before it sort of bleeds off the right amount of energy through various cobbled together processes to give you that perfect Planckian spectrum that we see on Earth from heated liquids and solids, right? So it's this kind of mystery zone. All of the light is actually made in the core in the standard model, the textbook model of the stars. That's the only place in the star where it's thought to be, you know, millions of degrees Kelvin, and you can actually have the collision energy necessary for this fusion to take place. And of course, fusion, like we talked about earlier, is how the stars are thought to be powered. Now, things get a little bit more interesting with the liquid model because we don't have to depend on the core of the star to be the sole place where fusion might occur. I'll get to that in a little bit. But with liquids, especially with this particular layered liquid, we have the opportunity for fusion to be happening kind of everywhere in perhaps less quantities than are thought to happen in the standard model in the center of the star. Okay. So these granules, right? This is what we can actually see, and they last, anywhere from 10 minutes. Some of the like ridiculously large ones, like thousands of kilometers across granules can last for a whole day or something like that. I mean, they're like the size of 2 Earths in width, basically, some of these granules. So they can last quite a while. But they're basically little bubble zones, right? They're kind of something from the inside is bubbling up. So that brings us to the thing on the right-hand side of the screen. These little holes that appear all over the place. Now the holes, these particular holes, they're called sunspots. You can see these, actually. I think we had mentioned when it was really smoky a couple of summers ago, you could actually look straight through the smoke and see the surface of you can see the photosphere, and you could see the sunspots migrating across it. Now, in periods where the solar activity is really, really strong, there's lots of sunspots. Periods where it's weak, there's almost no sunspots, sometimes no sunspots at all. So they're deeply tied into this magnetic cycling that the sun does. And in fact, sunspots almost always appear in pairs, which is quite interesting. And the pairs often have opposite polarities too, which is quite interesting. We'll talk about that a little bit later. So, of course, the standard explanation for sunspots, and actually this is an interesting situation where I could see both pieces, both theories kind of addressing being right in some part. But the standard story is, of course, there's a ton of magnetism associated with these sunspots for technical, complicated mathematical reasons in the standard model. And in the liquid model, I'll provide you a more material basis for why there's a lot of magnetism associated with it in just a second. But the idea is that there's all of this convection happening right below the sunspots like this, right? Because the sunspots, the edges of them are so magnetically active that magnetic motion actually suppresses the convection. And this leads to less bubbling up in the sunspots, and the sunspots are colder. That's the standard textbook model of how this happens. Now, with the liquid model, it happens a little bit differently. So with the liquid model, we have this idea that there are layers of this there's layers of this liquid. Now that sounds kind of crazy. I drew a picture of what this might look like before with these layers, right? So most people are like, layers of a liquid, that's insane. Well, we know this happens with water, actually. I wish I'd gotten you guys a picture of this, but one of the things I worked on when I was doing my PhD was this really crazy kind of microscope, which is just a little nano cantilever that you can actually push on things and feel the forces. Well, what you can do with these experiments is you can actually go down to the bottom of a jar of water, and you can actually feel little tiny steps of force as you punch down through each layer of water near the surface of a liquid container, basically, right? So we know that water actually forms layers, like individual planes, actually hexagonal planes, just like graphite or some of these ideal black bodies are constructed out of this hexagonal lattice of atoms. The same thing can happen in liquids as well, particularly in water. That's the one we've experimented with the most. So the liquid model of stars actually has a very similar hexagonal lattice to it. And the idea is that these layers can trap other stuff in them. So we've talked mostly about how the star is mostly hydrogen. But what else is in the star? Yeah.
Helium,
A lot of helium, maybe a quarter, yeah?
and then other like denser metals.
Yeah, basically everything else a little bit too, which is kind of crazy. And we'll talk about theories of why it has a little bit of everything else too. Obviously, it's not making some of those huge atoms. There's just not enough pressure inside of the sun in either model necessarily for it to make everything. But it can make a lot of stuff, and it seems to eat a lot of stuff, right? So things are constantly hitting the sun. Things are constantly getting eaten by the stars. Sometimes they eat whole planets. We don't know if that ever happened on Earth, but they eat asteroids, they eat comets. They're taking in all of that food and digesting it. Presumably it's ending up inside of them. Now, the interesting thing about a layered-like lattice liquid is that as it's under all of this pressure, it tends to trap those extra atoms, those big, heavy, weird things, in between the layers of its liquid, right? In between these hexagonal layers. And as it squishes down, it actually wants to sort of, by density alone, just like those bubbles in your convecting liquid want to rise to the top, because they expand and they're taking up too much space. They want to expand. The same thing kind of is thought to happen in the liquid stars as well. They're actually kind of burping out these heavier elements. They can also burp out gases that have been trapped in them, that have sublimated inside of them, right? And so the idea is that as these sort of trapped elements rise to the surface in these convective processes, that the layers actually have a really high metallic property to them. But as they burp up to the surface, you actually tilt those magnetic planes on their sides at some point. And you've actually made these kind of vertical columns that are highly conductive and result in these magnetic loops that we associate with sunspots, very much similar to in the standard model, with the exception that as opposed to there being this restriction of flow due to suppression of this convection, actually the convection in the liquid model is really, really important because it actually drives these magnetic structures into this vertical upright position. And so I think in order to make sense of that, we're going to actually have to think about what magnets are and why the arrangements of the atoms into these columns are important for the production of magnets. And we'll get to there in just a second. I do want to make it through the structure, though, a little bit more first. Yeah.
So are you saying like when asteroids and stuff like fall into the sun, it kind of creates these pockets of impurities, and that's what floats to the surface to create sunspots?
Yeah, in some part. I mean,
Kind of like slag.
slag, exactly. That's a great example. God, I wish I'd thought of that. You guys know what slag is? Yeah, so anybody been around, like anybody working with metal or making not forging, but yeah, really just metallurgy in general. Yeah? A little bit?
Kind of.
Yeah. So this was a huge discovery for humans, actually. What's that?
It also happens with lava.
With lava, too.
That's
Yeah.
why I get really angry anytime some fictional thing shows lava and it's just red.
Yeah.
There's black. It's all throughout it, and that's always usually the impurities.
The impurities, yeah.
To
They're excluded to the surface. It's such a good example, yeah.
oil on water.
Yes, yes.
It always goes to the top.
Right. So we have two things. We have impurities that are excluded by density principles. We also have the possibility of gas bubbles sublimating. So while yes, we're arguing that the body of the sun is generally a liquid, there's also the possibility that at any moment inside the sun, some of that liquid could evaporate, so to speak. That's the best way of thinking about it. So it could go into the gaseous form. And when it does that, it creates more density issues, more bubbling, which is going to rise to the surface and aid in these processes that we're talking about. So, okay. Yeah.
Could the impurities also hamper convection in a similar form to the standard model?
Yeah, the question is, yeah, that's why I think that both of those models could have a role to play in this process. I don't see them totally at odds with each other. I guess the question that has yet to be answered for me is whether the sunspots are truly colder or not. I don't know that they are. And I actually didn't even make my final argument here because we spent so much time talking about metallicity and stuff. Here's the thing. The sunspots are really these magnetic constrictions. Well, it's highly likely that something that's more magnetic is going to be more metallic, because metallicity is defined essentially by your conductive ability, how much current can flow through a given cross-section. More current means more magnet, because electromagnetism are two sides of the same coin. All that's going to make sense by the end of class today. So what could be happening is that the sunspots are actually not just more magnetic, they're actually more metallic, which would explain why they're so dark, because dark things don't emit much at the normal, straight to your face, right? Head on, you have way more reflectivity from metals and way less emissions from a thermal standpoint. Does that make sense? So that would be the alternative explanation for why sunspots are dark. Could they also be cold too? Maybe. I don't know. I'm not sure. I don't think that the evidence is there to say one way or the other, although it's very, very buried because, yeah, nobody wants to talk about that. Yeah.
If the sunspots are colder, that could explain with them being metallic why they're as dark as they are in comparison to the rest of it. Because I would still think even if it's metal, that the metal would still glow. Or at least
I mean, it's definitely glowing. Yeah.
like so dark in comparison. And yeah.
Yeah, it's weird. The field strength is extremely intense for sure. And in some sense, the surface of the sun there's other reasons to believe, which we haven't totally gotten to yet, that the surface of the sun may not have the most metallic of this liquid hydrogen. It may not be as metallic as other parts of it. Now, keep in mind, when we looked at that ideal black body, you know, that fingerprint of the rainbow that we see from the light from the sun and that we can make by heating up these experimental objects in the lab, which are called black bodies, those are made out of graphite. The really nice emitting ones are made out of graphite. Now, graphite's, of course, also a layered hexagonal lattice, right? But graphite is actually a pretty crummy conductor. It's a really good absorber emitter, but it's a really crummy conductor. It's not that metallic. So they don't necessarily go hand in hand with metallicity. Metallicity is a sort of side attribute that doesn't have to accompany great emissivity. So this is a little bit nuanced, but you can't think of them as the same exact thing. Okay, so right about, yeah, Kevin.
So, and maybe you're just getting to this, but if sunspots are this like, I guess, rejection of the impurities, how does it seem to like have this cycle of solar maximum and minimum?
Yeah.
Like convection.
We'll answer that question. But we need to understand how the sun's magnetism works before we understand why it flips polarity, because that is a really, really interesting open-ended question. And there's a few different theories for that. There's one that I like the best, but we'll talk about them. And then once we look at that, then we'll understand, we can come back to this liquid model and try to understand why sunspots appear so often at the height of the magnetic activity. I think it'll make a lot of sense if we can make it that far. I think we can do it. All right, so right above the photosphere, there is this interesting region. I think of it as the sort of cloudy region. If the sun was analogous to the Earth, we would have, you know, let's say the oceans at the surface, and then we would have a cloudy layer above it, right? So this is called the chromosphere. The chromosphere is also very, very intricate. There's a lot of beautiful structuring of these clouds. Now, the funny thing about clouds is, clouds, liquid or gas?
Both.
Yeah. That's what's really interesting about clouds. They're usually seeded with little chunks of ice. And of course, chunks of ice is condensed matter, right? It's atoms that are stuck together, molecules of water that are stuck together. Again, in a hexagonal form, which is quite interesting. But clouds are kind of where the rubber meets the road, right? They're a little bit of both. There's vapor state, there's gaseous elements of it tied up. They're very, very much this transition region between gas and condensed matter. And so I like to think about the chromosphere as possibly a similar situation. There's these beautiful, this is of course a loop that goes around between two sunspots here. This is really, really beautiful picture of this stuff that's called I think they actually call it coronal rain because it extends so high up beyond the chromosphere into the corona, which is the atmosphere of the sun. But you can see these very beautiful little droplets raining back down to the surface of the sun from some of these loops sometimes. Now they're very, very interesting. I mean, they behave very strange. They actually fall a bit slower than the gravity of the sun itself. So it seems like there's some sort of magnetic processes holding them back. But it does appear like they're kind of a condensate, just like the rain that comes down to us on Earth. I mean, you might have noticed, I don't know, I grew up in the Midwest, and it is super, super, what would you say, swampy in the summer. So with the humidity, the relative humidity of the air can get up into like 80+% saturation, right? Now that's weird because it feels really wet, but you don't see clouds in front of you when you're, walking down the street, right? Because that water is still in that gaseous state, right? But what happens when there's a thunderstorm or a rainstorm?
Now,
It condenses out of the air, right? And it falls down to the earth. And so it seems like something really similar is happening in the corona and the chromosphere as well with respect to some of these structures. There's more of these structures too that aren't quite as dramatic. They're called spicules. They're looks like these little columns. In many ways, they seem to very much resemble the same kind of condensation process that's happening. So to understand why there's so much, let's say, gas of hydrogen and helium in the corona, in the atmosphere, where's all that coming from? Well, we have to start thinking about processes that could generate that. And ultimately, that ends up as solar wind, which is flying out and bathing the whole solar system. But for whatever reason, it seems like some of those molecules are condensing out in these structures that we see in the chromosphere, which is quite fascinating. There's another little piece I wanted to mention. This is, by the way, the corona. So this is that, this is during a solar eclipse. It's blocking out the surface of the sun, but you can just see the atmosphere and all of its beautiful magnetic organization. This is a really weird feature. So if you look, this is, I think, from your textbook too. If you look at the temperature profile of the sun, this is the height above the photosphere, right? So there's the photosphere, chromosphere is above it, and then the corona extends out. And you look at the temperature. What do you notice that's pretty bizarre about this? Back of the room? What's weird about this? Temperature versus distance from the surface. Yeah.
It's like colder the further in.
Yeah, it's colder the closer you get to the surface of the sun. And it's millions of degrees really far away from the surface of the sun. That's sort of like if you had an oven that you put your hand into to take the bread out and it charged your hand, but the walls of the oven were ice cold. Weird, right? Now, I actually had the pleasure of here. Yeah, go ahead.
also that it's normal. It's what I would thought up until you get to where they label photosphere, and then suddenly it goes the other direction.
Yeah, yeah.
That's
Photospheres are our surface, right?
yeah.
So this is pretty bizarre.
So wait. So is photosphere everything beyond like to the left of the photosphere on that image?
Everything to the left is the interior of the sun.
So that's like extrapolated.
Yeah, sure.
Okay.
Yeah.
Sort of lost what I was.
It's okay. Stop me if you think of it. So this is really, really weird. And actually, I always thought this was weird, but it got less weird for me when I had a chance to talk to the leader of the team that built the only satellite which has gotten anywhere near the sun. It was called the Parker Solar Probe. So the director of that project, her name was Nikki Fox. We had her on the podcast a few years ago. And it struck me in the middle of that conversation, she was talking about how they flew their probe. They didn't get anywhere near the photosphere, but they did get into the corona. Now, the corona is supposed to be at tens of millions of degrees, okay? And I asked her, how in the world did you fly a spaceship into a region of the sun that's tens of millions of degrees? Any ideas? Yeah.
Is it that like hole on the bottom of the sun? Or like the
No, they went right into it. They went right into it. Yeah.
They go really, really fast, and then they're no longer in the really hot region.
That's you're very close to the answer. The answer comes down to actually how we define temperature, which is pretty funny, actually. So how do you guys think about temperature? What does it mean when something has a high temperature? It's hot, right? What is the scientific definition of temperature? Yeah.
atoms vibrating at different like speeds.
Yeah, really anything vibrating. I mean, like I said, it's really shocking, but we don't actually have a physical atom in modern physics. We have a mathematical atom. So temperature is defined as the average kinetic energy of a particle. What is kinetic energy? That's a big fancy word for how fast something's going. So when they say that the temperature in the upper corona is 10 million degrees, they mean that the average kinetic energy of the stuff there is really, really high. But guess what? There's almost no stuff there. There's almost nothing there. There's so few atoms per unit volume that you can get hit by one of them and you wouldn't even notice. You're still going to be freezing cold. Now, maybe your DNA is going to get cracked open. It might not be good for you to hang out in the corona for very long. But despite the fact that its temperature is in the millions of degrees, it's pretty cold, actually, it turns out. Yeah, Kevin.
How thin is the corona in terms
I wish I had a number for you off the top of my head. Actually, maybe I did write it down.
Didn't you say the corona extends like 2 solar radii from the surface?
It's about 10 to the 13 times more thin than the atmosphere of the Earth at sea level.
Oh,
So it's far, 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 far less dense than the best vacuums that we can make on Earth for industrial processes. It is
Very thin.
so empty. It is so much more empty than we can even
when you
conceive of.
then you don't mean like how far its range extends.
No. It extends quite far. I mean, how much stuff is there?
Um,
So again, let's go through this because it's really, really funny when you see it. Yeah, Zach.
So does the problem as you get closer to the sun become the fact that there is now more stuff, so it is technically hotter and hotter the closer you get?
The word hot does not figure into physics or science, hilariously enough. Yeah, but it is true. You're absolutely right. So the surface of the sun, the photosphere, its black body temperature is something on the order of 5,800 Kelvin, which is,
Little toasty.
pretty toasty. It might be a little bit hotter than that because there's convection, which is taking away some of the energy too. So all we're seeing is the temperature of the rays. So some of that energy is going into other processes as well. So it might be hotter than that. But it's not that hot, honestly. Those are not unachievable temperatures here on Earth. The atmosphere's temperature reflects the average kinetic energy of the particles within a given volume. There's almost no particles, let's say no atoms. I really hate the word particle. We can get into that some other day. There's almost nothing up there. There's a little bit, but almost nothing. Yeah, Evan.
If the heat or et cetera is reflecting the energy, if the particles are so few and far between, why is the temperature considered so high in comparison to the surface of the sun?
Because you're just taking the average motion of those very few particles.
Huh.
So it's kind of like, you know, I can't think of a good, I hate analogies anyways, I shouldn't do that. You can have a couple of atoms speeding around at gazillions of degrees temperature, but since there's only a couple of them, they're not going to warm you up. They don't have much material in motion. They have a lot of motion, but they don't have any material. Energy is always the amount of material in motion, the product of those two. So you can have a lot of material and a little bit of motion. If you got hit by an aircraft carrier up against a dock that was going 0.5 mile per hour, you would still be splattered because it's a lot of material with a little bit of motion.
Sure.
Or you could get hit by a jet ski going 50 miles an hour against the dock, and it would also splatter you, right? Because it's a little bit of material, but it's going really, really fast. Same thing is happening in the corona. There's a very little amount of material. It's in a tremendous amount of motion. Yeah.
And that, I guess, makes sense in this with temperature being like how temperature is transferred is that energy, that motion, that vibration being transferred. It's much harder for a single particle to try and change the inertia, right? To fight the inertia and change the momentum of a whole human body,
Or a whole spacecraft.
something that is trillions upon trillions of atoms
Yeah.
trying one or two particles atoms trying to
Yeah.
versus a gajillion
Yeah.
atoms on the surface of the sun.
Yeah.
That is maybe relatively way slower than that single particle, but is relatively much faster than the human body or the spacecraft. So it's able and much faster. So it's able to transfer that energy.
That's exactly how you should be thinking about it. Kevin, yeah.
In that transition region, I'm noticing there's that like little jump and
Yep.
plateaus, and then it spikes for the corona. Why is it like that instead of it going, more smoothly? I guess into the corona.
I mean, my suspicion is that there's a lot of condensation in this region. There's a lot of rain and clouds and things like that are sopping up a lot of that motion. So those condensation reactions take a lot of energy out of the system, basically.
So that's why it like plateaus for a little bit before going into the corona.
And then the atoms that actually end up escaping still and are getting accelerated by these magnetic fields and everything, they actually are moving quite quick, is what it comes down to. Yeah.
Aside from the point at the photosphere to the left of that,
Mhm.
everything to the right looks like a graph of the average density of Earth's atmosphere.
Mm.
Just realized it at like the
I'd have to actually pull it up.
part of Earth's atmosphere, the density of air, they have those sort of plateaus between different between the like there's a spike of just it going basically inverse, so there's way less density at a certain point because of the clouds. When you go beyond the clouds, you'll notice this if you climb a mountain. You go beyond the
It looks like it's a smooth transition, at least when I just Google it and look at a graph of it. It looks like a smooth transition. Yeah. But
okay.
yeah, that's a conversation for another day. I'm kind of hell-bent on being able to explain magnets to you guys today, so I think we should jump to there next because we won't be able to answer any of our questions about the solar cycles without understanding magnets. So I think we should do that. Last thing, I guess, I did mention this at the end of class.
Sufas?
What's that?
Typo.
Sufas.
Hey, nobody's perfect. The SUFAS motion. This is something that's actually quite funny in terms of the argument that the sun actually does have a surface. The motion of the photosphere is orthogonal in a completely different direction to the motion of the corona. Corona also does rotate. It rotates at a very different speed than the photospheric surface of the sun, which is quite wild. But in general, their vectors are orthogonal to one another, and that makes zero sense if the thing is supposed to be a continuum of gas. But all right, let's go on to talk about magnetism and the solar cycle and all of this business, because this is really, really important to the future of the Earth, I think, particularly our technological civilization that depends on functional electromagnetics and telecommunications and all that stuff. So I think this one's from your textbook. It's a bit outdated now, but you get the basic picture. You're looking at a full cycle here from minimum to minimum between 96 and 2006. So, you basically have this it's approximately a decade long. Maybe 11 years is more accurate for the real peak to peak. This is actually the intensity. I believe that, what is the x-axis here? Sunspots, which correlate. That they kind of tell us how magnetically active the surface of the sun is at any given moment. And this is going back from 1998 all the way up to the present, more or less present moment. I guess it only goes up to 25, but welcome to 26. And you can see that we're basically at a peak here. We're maybe coming off of a peak from last year in terms of sunspot numbers. And so, these are really, really mysterious phenomenon that happens. It's very predictable. It's very regular. There's a few things associated with it. We know that during a given cycle, the sunspot pairs actually tend to have the same polarity in one hemisphere versus the other. And then after the polarity reversal, after the cycle is complete, you will see the polarity, the north versus south of each one of those magnetic pairs, is completely opposite. So the whole sun is going through this transformation where the north becomes the south, magnetically speaking. Okay. And as that happens, the magnetic field gets super chaotic, twists up, and eventually you have this complete rearrangement of the solar magnetism. Yeah.
Earth has its magnetic poles also shift, but ours takes like hundreds of millions of years, doesn't it?
I think we don't know for sure, but probably on the order of a million years. Yeah.
I could be incorrect, but I thought I heard once there's around every 200,000 years.
I think the last one was 700. You guys can just go or ask one of your chat bots or something. I think the last one was 700,000 years ago. In all honesty, it's a bit of a, nobody was around back then to take measurements, so we're depending on a number of indirect ideas to get us there. We don't know totally, but it seems like it's very infrequent compared to the sun, which we can literally watch happening, right? So since humans have been recording these cycles, I think this is our 25th cycle that we've just come out of, basically, that we've have records of, and we have, zero records about the Earth's magnetic pole, basically, at least first-hand records. Yeah.
Do we have any evidence of other planets shifting their magnetic fields?
I believe so, yeah. I think that there is some evidence that Mars, for instance, which is probably one of the best studied surfaces that we've been to, well, not us human beings, but we've got lots of probes there, rovers and stuff. There is, basically what they look at is they look at the imprint of the magnetic field on the rocks. So some of those rocks are iron, and just like, you guys ever magnetize paper clips when you were bored in elementary school or something? Yeah, so you can magnetize iron. You can turn it into a magnet just by basically dragging a permanent magnet across them. Same thing happens with rocks, and so that's also how we infer the presence of these magnetic cycles on Earth in the past too.
Notice we permanently we do it a lot in most of the evidence is on the surface of the ocean.
Surface of the ocean, yeah.
Like the actual floor of the ocean, I mean.
It is true.
Because there's these lines that at some point that point toward one pole or the other, like a compass, and then suddenly they point in a different direction along this line.
It is true.
Yeah.
Okay, so let's talk about magnets. How the heck do magnets work? We're particularly interested in a very primal version of a magnet called an electromagnet, because the sun, neither myself or anybody else is arguing that the sun is a solid body. We think that it looks like a liquid, it behaves like a liquid. So how in the world do we produce magnets? What the heck is a magnet? How does it work? What I'm gonna have to do is ask you guys to go back and start thinking about this atom that we talked about. I built out this atom for you guys. Can anybody remind me about the atom that we talked about a couple weeks, or maybe a week or so ago? What were the basic features of that atom?
The hairs.
The hairs.
The filaments.
The filaments. I appreciate you nailed the terminology there. So this is kind of an older picture that I've drawn, but I think that it will get the basic idea across. So on the right-hand side, we have the atom, right? We have the electron distribution function, which is, again, from the mathematical atom that we are granted by quantum mechanics. We have this idea that the surface of the atom, the electron, can extend indefinitely. This is where we get this model of the hairs from, right? I call them filaments. But we think that the atom is best thought of as a structure that has a really thin but connective atmosphere to it, which is quite hairy in some sense. This is how we model it anyways. Now, the cool thing about that is that it allows us not only to have a way that atoms can communicate with their neighbors and maybe in groups to relay things like light, but it also starts to help us make sense of things like magnets. So if we put a bunch of atoms end on end and we make a wire out of a single column of atoms, right? Then the conduction of electricity is just the motion of the surface of one atom being transmitted to the next. And of course, it's going to go down a charge gradient where charge represents how much energy, how much motion is in the surface of one atom with respect to another. And so the conduction of current is really just the transmission of that rotatory motion down the line in the wire, which is what I've tried to draw for you here.
A single atom wire.
A single atom wire. It's completely ridiculous, but it allows us to simplify our picture of what's happening. And so what falls out from this is that the electric action, the electric field as it's described, is orthogonal. It's the motion of the direction of that transmission of motion from one atom to the next, while the magnetic motion, which is coupled to that electric motion, is really just the equatorial motion. It is literally the motion of those extended structures from the surface of the atom as they are transmitted laterally. So it's literally this kind of spinning motion of the extended surface of the atom out to the side, right? So atoms, when they're just all flying around whatever willy-nilly, let's say in a gas, these simple hydrogen atoms, their magnetic motion is all different. It's all over the place, right? There's no cohesive magnetic property to this neutral gas. But if I drive a current through that, if I basically put these gaseous atoms inside of a tube and I hook up, basically drive a huge amount of motion at one end, and I have the same motion but a lot less at the other end, so a plus and a minus anode and cathode situation, what I can do is I can organize all those gaseous atoms to actually start to spin in a concerted way together, and they actually can align and form a little wire between those two poles. That's essentially what's happening the way that we model this inside of something like a vacuum tube or a cathode ray tube or a fluorescent lamp even, although that's a little bit more complicated, but inside of, let's say, a discharge tube of any sort. So the point is, part of once you've done that, once these atoms are all working together, even in this gaseous form, they're aligned, then they start to take on a shared magnetic direction. They're all aligned, right? The alignment is everything when it comes to understanding magnetism, okay? Now, how does this play out? Well, why do they attract one another? Well, what happens is that when you have two columns, let's say two single atom wires, now all of a sudden, not only are you able to align all of those atoms, but when they're aligned together next to each other, then they're all sharing the same direction of motion of their surfaces. And you get an even more amplified version of that same motion because everybody's spinning and turning in the same direction. So if you turn the columns around, so they're going opposite directions, now they're actually batting against one another. Those columns are actually pushing away from each other, which is in some sense what I've drawn in this bottom panel versus the central panel. The columns, their electricity is going in the same direction when they attract. You could do this with wires too. Drive a current through a wire, you'll actually see there's a small attractive effect between them. When the wires, you turn them the opposite direction, they push away from each other just a little bit. This makes sense given this model that I've given you guys. Now, if you want to make a really strong magnet, you don't just take a single wire. You actually do something where you coil that wire up. Why does coiling it make an even more powerful magnet?
Because you got more material in the same twist.
Yeah, you're basically aligning those equatorial zones with one another. So the current's going sideways to the coil, but that means their magnetic action is all aligned the same. So you actually have a situation where they're all rotating in the same direction, right? And this creates an even bigger, consolidated, like cohesive action where all the atomic shells are all moving together in this really beautiful orchestrated fashion. This is called a solenoid. The solenoid is at the heart of what we think is happening inside of the Earth and inside of the sun. The difference being that they're actual liquid flows of these atoms. Let's think about the Earth for a second, since nobody doubts that the interior of the Earth is a liquid. Inside of the Earth, you actually have, because the thing is turning, you get these things called, you get swirls, basically, as the thing is turning. And the result of it is that you actually organize these atoms into these solenoid structures. Yeah.
Eddies, right?
Yeah, they're sort of eddies in some sense. And the technical term for this is Coriolis forces that organize it into these swirls. Not that that explains much, but you can imagine just spinning a bucket, you're going to make these little swirling eddies, exactly. So this is what we think about in terms of the way the Earth does it. Now, yeah.
Is this what led us to believe that the Earth's core is iron and nickel and all that? It's metallic.
There's a lot of arguments for that. But yeah, that is a huge part of why it's capable, in theory, of doing this magnetic stuff. It gets really, there's so much more complication to this, and I'd be happy to get into the details of it maybe next time. Of course, if you were to go and build a solenoid, I have one that I like to bring to show you guys how this works, but I forgot it. Sorry. One of the things you do if you build a solenoid yourself, they're really easy to build, just coil this wire, is that the wire has to be insulated. Because what happens is that if the coils are able to just conduct straight down, then all the cohesion falls apart. It's not able to actually get that spinning current system that's actually able to organize the magnetic field. So the wires are insulated from each other. Now, that's really weird because you might think, how in the heck are these eddies insulated from one another inside of something like the Earth? We haven't even gotten to the sun. Any ideas? Well, at least inside of the Earth, the nice thing is that it's not just nickel and iron. There's actually a bunch of other junk in there too. There's insulating atoms. Now, the difference between a conductor and an insulator is the same thing that's different between a metal and a non-metal. In other words, those atoms don't want to be realigned for whatever reason. And it's probably beyond the scope of our conversation to imagine what actually atomically makes the difference between a metal and a non-metal. Maybe they're not able to bond as well with their neighbors, even when they're driven really, really hard from below. Maybe they resist being reoriented. Maybe their electron shells, their surfaces, are just not amenable to that kind of contact symmetry, so they can actually form these nice little building blocks with their neighbors. There's a lot of reasons why that might be happening. But it seems like inside of these planets and inside of the stars, there are insulating elements. Now, when it comes to the star, we're actually talking about breaks in the lattice of the material that make it less metallic, right? So that it's not able to conduct as well. But it's a really extraordinary feature that it's able to self-organize just based on these swirling liquids. Now, the cool thing is, it's not totally theoretical. So people can do this in a lab. They actually can make these exact same type of magnets with, basically with model planets. How do they do that? What do they use to do this? Does anybody know? Of course you don't know. This is super esoteric. They use molten metal to do it. They use molten sodium usually to make these, right? They're called little geodynamo models, right? And they actually have to imprint them with a magnetic field to get that pattern organized in the first place. So it's pretty extraordinary that when we try to do these on Earth, we actually have to use a liquid metal to make it happen. And that is exactly what we think is happening in the sun. Now look, I am basically out of time today, and I didn't get to talk about the core. I didn't get to talk about why the sun cycle happens and why this reversal of this polarity happens. But at least we have a basic floor plan for how the magnets themselves work. And I think that's going to lead us nicely next time into talking about how that solenoid could be reorganized periodically. And it has to do with our model for what's happening at the core. So let's pick up right there next time. And yeah, we'll continue the drama. You guys have a good week, and we'll do it all again Thursday.